Alright, so here we are with Unit 6, Lesson number 5, and we're going to look at the measurement of heat energy. Remember we said in the previous lesson that heat energy cannot be measured directly. You can really only measure changes in heat energy. And what we're going to be looking at in this lesson is this formula right here at the bottom here. Let me see if I can get my pen to work. I may not. Okay, let's use blue. Alright, so what we're going to be using in this lesson number 5, is this number here, and we're going to be looking at this formula. That's lesson 5. This would be lesson 6, and this would be lesson 7, so we're not going to look at those right now. But here's the formula. Remember, Q is heat, and that's measured in joules. M, you can see, is the mass of, in this case, the water. Delta T, this means delta, that means change in temperature, and C is the specific heat of water, and that's the value right here. So C is this number right here. You only use this formula when there's a change in temperature. So if you go back and look at the heating or cooling curves, mainly the heating curve, this is only used for sections A, B, C, D, or E, F. This one here is used during sections B, C because there's no temperature change, and this is used during sections D and E. So this will be lesson 5, lesson 6, and lesson 7. So let's go through and look at these. Okay, so the amount of heat given off or absorbed in a reaction can be calculated using the following equation. Every single chemical reaction and physical change as well involves either the absorption or giving off of heat. So they're either exo or endothermic. The formula, as we just saw on the previous slide, is on table T. It's Q equals mc delta T. And this explains everything that we need here. Specific heat is the amount of heat it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius. Every substance has its own specific heat. Water, for example, has a relatively high specific heat. Now, what does it mean? And you should probably write this down. If something has a high specific heat, that means that it takes longer to heat and longer to cool. So, for example, water, as I said, has a relatively high specific heat. So it takes a relatively long period of time to heat a sample of water, and it takes a long time for water to cool because it has a high specific heat. And again, the specific heat of water is found on table B. Now, let's take a look at calculating the changes in heat in a reaction. So here's an example. How many joules are absorbed? So you have to remember, of course, that if we're looking at joules, joules is going to be Q. You have 50 grams. Oops, I'm off the thing here. 50 grams of water is the mass. That's M. And here, if you look at it, is the change in temperature, delta T. So you're going to subtract 58.6 minus 30.2, and that's going to give you 28.4 is delta T. So you have the equation Q equals mc delta T. So what you're looking for is Q. We know that the mass is 50, that's M. C is the specific heat. We know it's 4.18. I'm leaving out the units just because I don't have the space. And you're going to multiply that by the change in temperature, which is 28.4. You multiply that out, and that will give you the number of joules of heat absorbed during this reaction. So there it is there. And the answer comes out to 5,940. Notice that they rounded off to a whole number. So that reaction absorbed 5,940 joules. Look at the next one. Now it says the energy is released. So that means that the energy is going to be given off, but it's the same process. We're using still 50 grams of water. The change in temperature is 10 degrees. So you have 50 grams of water times the 4.18 times the 10 degrees. That gives you 2,090 joules. Here's another question that doesn't involve the actual calculations. It says water goes from 289.6 K to 309.6 K. Is the energy is heat energy released or absorbed? Well, if the temperature of the water went up, that means that heat had to have been released. So that means it was an exothermic process, and we're not going to worry about calculating it. Okay? So that is how to use the formula Q equals mc